Anyway, the title of tonight's talk is the Circum-Atlantic and Gulf of Mexico deepwater oil plays pooled in coarse-grained classic reservoirs that are deposited in deepwater environments, current deepwater environments. The first slide is a night view of the Earth, and you can get an idea where all the oil and gas are being burned. You can see three things in the key. One is the magenta dots, or the dark pink dots. Those are the known Atlantic and Gulf of Mexico margin deepwater clastic hydrocarbon producing areas. The green ellipses are probable future Atlantic and Gulf of Mexico deepwater clastic producing areas. You'll see some red and green dots. These are other known deepwater clastic discoveries, including the North Sea, the ones offshore Levant there in Israel, and also the Barkentine discovery off Southeast Africa. So if you think about what we're doing here, this talk has a lot of scope. Expected to be about a 45 and possibly even a 50-minute talk. The ground rules for my talk. When I use the term deepwater clastics, I'm referring to coarse-grained clastics, sediments that are greater than silt-sized particles. I'm not talking about unconventional, semi-conventional plays, especially since we'll be dealing with deepwater discoveries. In other words, there'll be no Bakkens or no Wolfberry type oil fields in this talk. The deepwater clastics include carbonates and quartzose sandstones. The carbonates are grossly underplayed around the planet, and I will be talking about those, and I'll even talk about an opportunity that exists in the carbonates. Since my talk is a major regional talk, no individual field will be discussed at great length. If I started doing that, it'd be a 4-hour talk. In fact, this could be a short course, which is, I gave a short course that's an expansion of this talk in Trinidad. Most of the fields I discuss will be oil fields. Nobody's looking for gas at this juncture with $3 an MCF. There's just too big a discrepancy between oil and gas. Most fields that I ever discussed currently reside in water depths greater than 200 meters or 660 feet, which is the shelf margin today. About a few fields I discuss will be located either onshore or on continental shelves. I've done this basically because I set up some of the deep water plays that are now being made. Now we see influence of graded deposition on the slope to basin profile. On the top, you can kind of get an idea that we started in 1982 to 1992 in the shingled turbidites off the deepwater edge of the shelf, very close to on the slope. From 1992 to 2012, you moved down to the middle slope environment. Since 2005, you're in the basin floor environment with places like Jack. Now, if you're in the North Sea, you would have started out in a shallow, in a relatively deep water environment in the English North Sea, where they have Paleogene fans there. But where they're looking for the Paleogene fans now, they're much deeper in the water depth. You notice I got the 2A would be the low stand track shelf margin channels incised into the base level. And what really control these sands are the paleo base level. Modern day base level, when you see what appears to be a graded profile, if you don't get in cuts into that profile, you don't collect sand. It just keeps on. Once it hits the top of that slope, it keeps on going all the way to the bottom. We have incised areas on the continental slope and actually up on the outer shelf. You will collect in those incised areas. They'll backfill during the sea level rise and start filling with sands. So it's very important to know what your paleo base level is. Can't dwell on that too much. Next slide is early to middle Cretaceous, the greater Gulf of Mexico carbonate producing trends. The reason I'm discussing this, there's 3 giant field areas within the Gulf of Mexico. 2 of them are in deepwater clastics. The Golden Lane fields, I put that on there, not that it's deep water, but because it's very close to Poza Rica and it's related to it. Poza Rica oil fields, ultimate reserves there, about 2 billion barrels of oil. They're onshore in the onshore Gulf of Mexico area in eastern Mexico. And they were discovered in 1930. That makes that the oldest deepwater field in deepwater clastics in the Gulf of Mexico basin. It was found in 1930. That was about 60 to 70 years before they started doing things in the deep water off the continental shelf. We'll talk also about the Campeche Bay oil fields because those are bolide impact deposits. They're Cretaceous-derived carbonates, but they're actually basal Paleogene in age because that's when the bolide impact occurred. Here's an example of slide that basically shows the Golden Lane and Poza Rica area. If you look here, this is the Golden Lane province here. What it really is a paleogeomorphic trap. What's happened is, at one point in time, this surface was flat and went this way, and you were down dip in this direction, which would be the slope area or the debris apron for this giant carbonate bank. But what's happened here at the west, starting in the LARAMIDE time, you started uplifting the western margin of Mexico. And when you did that, it tilted this whole margin develop a sedimentary source over here that prograded and filled these and sealed off with distal deltaic deposits, sealed off the accumulation here in the Golden Lane, which is normally pressured. That was found in 1908. The showpiece for that trend is the Potrero de Llano number 4 well. It produced 85 to 90 million barrels when it blew wild by itself. It's almost a national class oil field, giant oil field by itself. You also have the Marine Golden Lane over here, which is seaward edge, which is not as good as this trend here. Source rocks down here, it's Upper Jurassic age. The onshore Poza Rica trends sit right in here, which is basically the debris that's been shed, has been shed to the west. If you were to consider what's going on, by the way, this cross-section sits right down through here. Here's your tectonic front over here. It's slightly off the cross-section. You have to kind of consider what's going on here. Hurricanes have been blowing from east to west probably since you started opening the Atlantic Ocean. And as the hurricanes blow from east to west, the northeastern part of that hurricane just starts stripping off carbon debris and shedding it off to the west. And that's why you have Poza Rica field. What this really is a giant stratigraphic trap, very gentle faulting because it's a foreland basin margin stratigraphic trap. We'll take a look at this trap. Here you are as a three-dimensional diagram, courtesy of the Mexicans. Gold Lane sits up here. It's called the Tuxpan platform, by the way, or toll. Here's all these Golden Lane fields in here. That encompasses more than 1 billion barrels of oil. Down here's Poza Rica, sits in the basin debris down in here. And here's what it looks like in map view. This is actually a structural map. Notice the very top of the structure's bald of wells. You just don't, bald of producing wells, that is. You have a water-wet syncline down here, and that syncline separates the oil accumulation you have here in Golden Lane versus the Poza Rica accumulation you have down in here. Now you go to an isopac map of the Tamabra facies, and you can kind of see where it resides. It resides from about 250, in fact, the 250 meter contour pretty well controls Poza Rica. So it's really a structural stratigraphic trap. It's just you uplifted the west, you tilted the old debris apron and formed a stratigraphic trap. It's relatively unfaulted. And what do these debris flow reservoirs look like? This is from Laux's article on Search and Discovery website. It's actually an excellent article. If you want to know more about this, I suggest you go to that website and check it out. Over here you can see what the Tamabra facies is. It looks to be basically sealed by deep water carbonates above it that do not have a lot of debris in it. Your source rock's down here. It's Pimienta shales down here. It's Upper Jurassic age. And I think they're basically equivalent to the Bossier shale we have onshore in the East Texas Basin. Here again, you've got the debris flows here, and what they've done is made geobodies here by going to the wells and creating thickness, so you get kind of a 3D diagram what the debris flows deposits looks like. And over here, you got the concentrated and concentrated flow deposits down here. The breccias were deposited by debris flows, where the grainstone and grainstone dominate packstones were these other ones over here. Then we're going down to Cantarell because it is basically a deep water deposit now. I'm discussing it, it's actually on the continental shelf, or if not the upper continental slope, very upper continental slope. It's in a relatively deep water shelf environment from what I know. I've not really worked Cantarell. But you get an idea of where the bolite impact breccias are. Now, Cantarell produces from more than these breccias, but this is the main reservoir in there. They call it Upper Cretaceous, but what it is, it's disintegrated pieces of the Upper Cretaceous that happened during the incipient Paleocene, or when that bolite impact occurred. Now, here's this map. Here is this map right in here. And over here is where the Chicxulub impact occurred. So it didn't take a whole lot of distance to go to put all these thick clastics over here. This is the main producing portion of the field. This is your main seal here. These are basically I believe salt cord structures, but they're basically involved with back arc thrusting and possibly some wrenching associated with this. You notice on each one of these slides I put a larger dot that shows where you are in the world. This keeps things in scope as we move around the world. We're going to cover a lot of areas, so I'm going to try to move fast without being really too fast. Again, Cantarell, there's a sediment cross-section across it, geological cross-section here. What they're really attempting to show here is Cantarell field sits here, and this is a very big field. It's like 13 to 15 billion barrels recoverable, especially now that Sahil's added in it. That's 1 billion barrels right there by itself. So it'll be about 13 to 15 billion barrels recoverable. And what you see is the overthrust and the subthrust. This is the overthrust area here, and you have oil here, even though I don't show it in this particular well. The Sahil subthrust down here, you get breccia that produces down in here. So apparently the fault plane does seal. This is taken from a PEMEX website publication. This is a seismic map, seismic-based contoured map with fields, the wells also on it. Hanging wall overthrust zone where it's producing in Cantarell, and this is a Sahel field over here. These two areas actually overlap. And now I'm backtracking now to the area over western Golden Lane, mostly over Poza Rica, because since you had a four-lane basin trough in there, trough that formed because the uplift of western Mexico developed a lot of slope sands here that become the Chicontepec sandstones. There's a lot of oil in these sands. Unfortunately, most of it's heavy, and the sands tend to be a tad silty, as I remember. And just the heavy oil and the combination of the slightly silty sands make it, there's a lot of oil pooled there, but trying to get it out is problematical. But you can get an idea as to how deep that Eocene nonconformity is cut down through here. This is from a thesis by Marta Castillo. Good paper. LARAMIDE uplift along the westward margins of the North American continent generated the massive PALEOCENE-EOCENE WILCOX sedimentary regression. Now down here you see the composite oil sands, but for some reason nobody ever foresaw that you'd have the WILCOX sandstones here. If you go around the planet, the same basic WILCOX equivalents produce a lot of oil and gas that are billion-barrel fields in the North Sea. And they made it down the slope, and people just never foresaw that. And finally, somebody who was drilling a well in the Gulf, one of the major oil companies drilling a well in the Gulf of Mexico, had a little extra budget made because their Miocene objective didn't work, so they just tried to take it down a little bit deeper and see what that extra reflection events it was. Turned out it was the top of all these massive oil-bearing sands. It just really changed people's opinion on the Gulf of Mexico. This figure is taken from Zara's paper. Very good paper, actually. We'll see a cross-section that kind of runs along the front, and here it shows all these oil fields. You get an idea just how expansive this oil trend is here, and actually it goes down into Mexico. This is just the U.S. part of it. They estimate there will be 15 billion barrels of oil come out of this trend that could be produced. This is a seismic cross-section down here, and a geoseismic cross-section above it that goes through Keithley Canyon, Walker Ridge, and Atwater Canyon. Here you can see Jack, St. Malo Field, Chinook Deep, Cascade. These have all been found since the original discovery. Notice how thick, even on this very small scale seismic section, how thick that sand section is. It's extremely thick, and we'll see it on the next slide. This, by the way, is a 2007 slide taken off Zara's work. Take a look at this scale in here. I believe there's a lot of pay in there, many hundreds of meters. 350-foot net over here, 600-foot net over there. Again, they call it net because you have to kind of look at the sands are somewhat silty. Notice that basically you have an overlying salt seal that basically forms a lid in the kettle, but actually the actual seals up in here is actually the overlying transgressive system track shales and limestones. And here's what the Jack extended test looks like. It's got gross thickness of 815 feet. You got a lower zone they perfed. They got oil out of that. They didn't perf this area down in here, and they didn't perf this area up in here. They did perf this up in here as well as the middle zone. They did not perf this sand here nor this sand here because they fracked it so hard when they tested these other zones that they damaged the seal. Consequently, they really didn't want to damage it anymore, so they didn't test what shows to be some of the better sands in the sequence here. Even then I think it flowed like 6,000 barrels a day. And then show the fractured limestone at that depth there. So we go on next. It wasn't just the WILCOX we made discoveries on. Actually, before you had the Deepwater WILCOX discoveries, you had the Miocene discoveries. One of the showpieces for them would be the Thunder Horse Field. You notice there's a location down here. Mississippi Delta, I believe, is up in here somewhere. But it's actually on the outer continental shelf. It looks like actually on the slope, if I'm not correct here. There's 1,000 feet for scale. Look at the thickness on those sands. They're really thick. They're boxcar sand. They're extremely thick. EURs in this field, they thought it would be about 1 billion barrels. I think they've actually tracked it back down now because the problems they're having with it may end up being like 700, 800 million barrels. This is taken from Lipinski's GCA-GS 2004 paper. Okay, moving around, where's the best place to look for carbon play? Well, it's going to be probably around the Bahamas. If you think about the hurricanes blowing from east to west, then the debris apron would have been shed down through here amongst many places. And look at all the wells that have been drilled down here. They all show oil shows. These are live oil shows. They're not just dead shows. So, and Bahamas Petroleum is making a play down here and owns a lot of the acreage in here. And unfortunately, Bahamians, after they had Macondo disaster, got cold feet, and they're kind of trying to convince themselves they need the oil more than they do the tourism. That might be a tough thing to do because I love swimming around the waters. In 1958, Zapata, owned by Howard Hughes and George Bush, led the Quesal number 1 well. That's this well here, I believe, here that got the live oil shows, 32-degree API down through here, and mostly in the Cretaceous section, I believe. What do the structures that Bahamas Petroleum Company look like? Here's what they look like. These are massive structures. I mean, really big. The contour interval is 0.1 seconds or 100 milliseconds. And look at all the contours you're stacking up there. 25 kilometers for scale. We go back down and we say, well, what do they look like in cross-section? Look at the size of these folds. Look at the hydrocarbon seeps coming off the top in there. Does anybody think there's no hydrocarbons in them? I suspect there are. You can actually see a pockmark that's come up from a hydrocarbon leak up in here, too. And some minor zones over here. It looks like there might be something. This is this fold. This is this fold in here. Anyway, yeah, it looks like they've got a good place to be looking for oil and gas along that area, most likely oil. Now, as we travel from this area here, that's where the Bahamas were. We're going to travel around. We're going to go through Trinidad and Tobago on our way to Brazil and also through Suriname, French Guiana. What this appears to be, and this is taken from Mann, Bingham, and Escalona's paper in 2008, this is the Caribbean plate just literally furrowing its way or plowing its way into the crustal plate that represents the Atlantic plate here. And of course, there's your volcanic ridges back here with your outer arc. Tobago sits at this end of the arc. It sits off the Orinoco Delta. It's actually the best place to look for oil and gas. You got great source rocks in Trinidad. It's a supercharged province. If you can afford to get in Trinidad, it's a very good place to go. They've also had some discoveries in Tobago, but the problem there is getting continuous sandstones. But the source rocks tend to extend out that far. Okay, this is from a paper that will be given, I believe, in March or April. This is from a paper by Xavier Moonen. Right here, the guy with his hands up. That will be given by the international group. I'm working in this area right now with Xavier. I work the area offshore here in the Gulf of Paria. Found some relatively large oil fields over there. I'm working with them now, mapping this area on 3D. What you see here is a series of primary shear zones, because what happens up in here is the subduction zone and the fault you get associated with the subduction fault splays out and becomes giant primary shear zones that run down through Trinidad. The last of them, I think, is down through here. And where they have those giant shear zones help determine where the oil and gas is. Most of the oil tends to occur right in here. There's some actually north of this area up in here around Tobago. A lot of gas condensate down in here. The question is, why is there more gas condensate? Is oil here? It could be related to type source rocks. Another slide from Mr. Moonen's paper. Just gives you an idea of what these things look like. This is Barrick Pore Field. This is a 200 million barrel field, and it's at reasonable depths. It's not. In fact, I guess 2 seconds down there shows you how reasonable it is. It's a series of fields, not necessarily one, but it's really Barrick Pore, penile trend. Actually, the subthrust as well as the overthrust both works. Remember, your topic Cretaceous sits down in here, and down here you have Naparima Hill source rocks, which is an extension of the East Venezuelan source rocks they have here. Both East Venezuela and Trinidad are supercharged petroleum systems. There, what you're looking for is a reservoir and structure. You're going to find something. It's just a question of how much. Now you go offshore and you see what appear to be some tertiary toe thrust folds out in here. Up dip growth faults, translational midsection here where you have some mud diaprism. Out here you get the ramping up toe thrust faults down through here. The attachment surface at the base of the front, Cretaceous, top of Cretaceous in here. Your source rock is going to be in here. Really the question you have to ask yourself is, has the oil that's coming here leaked up into these channel sands and basin floor fans that have been involved with these toe thrust fronts out here, or do you have gas condensate? And that's going to be a question of source rock and migration history that has to be worked out. I've not really worked this area, but I'm familiar with the basic play. We're going to see how all this works when I hit Zafiro, because that I basically understand. Now this is the geophysical section. There's a geological section. Now we've worked our way around to off Suriname. Suriname sits here. We're working really our way toward the Zadisis discovery made by made by Tullow and others in 2011. They actually bought the acreage from somebody else who actually foresaw this over here. They had the acreage, and so Tullow bought the acreage from somebody else who basically had the play concept. We'll also, okay, I'm sorry, I'll speak up. We'll also talk about the Venus B and discoveries over here, and we'll also talk about Teak and Jubilee. Over here, Tom Rager Field's about 900 million barrels of oil in place, but it's only 15.6 degree API crude. And really, what this is, these are in this field is pooled in the up dip equivalents of the WILCOX and Chicontepec sandstones. They're paralic sandstones. Again, now we're down right in here, so you get an idea. We've traveled from here all the way down to here. And there's what the field looks like right in there, lower tertiary. Now I should go back a second. This would be Zedice's field, it's just right here. You can see there's a shear zone that runs here from Ghana all the way over to French Guiana. And so it's not a large projection when you recreate back the two plates to go from Jubilee, which is about 1.5, 2 billion barrels recoverable to Zedice's. The problem with Zedice's, and I'll be up front with this, and also the play you have in nearby Guyana in Berbice Canyon. The problem with this play is you've got a midsection overpressured zone, a lot of overpressured shale with some sandstones in them. You got to drill several thousand feet, if not more, of overpressured material. You go from normal pressure to overpressure, and then you come back into normal pressure below that. Well, every time you have those pressure zones, you pass through those, you're talking about pipe points. So you have to have a very good pipe program to be able to get all the way down to the objective. And even then, you talk about $300 million per well. And it can be quite expensive. So you're going to have to be able to get large reserves, connected reserves like what you have over here in Jubilee Field to make it work. They drilled the discovery well and they offset it somewhere out here on a little bit different structures, ACES 2. They deemed that to be non-commercial, basically probably for what I just told you. But that's just my suspicions. Okay, now we're moving down to Brazil, and we'll talk about unconfined and confined coarse-grained clastic plays. Here is the Oligocene shelf breakdown in here, and you're getting some Paleogene sandstones down through here. This is taken from Carlos Brune's paper, which was given the APG. It's a distinguished lecture, and it's actually a very good paper. The guts of it are on the APG Search and Discovery website. I would suggest if you want to really understand Brazil, take a good look at the seismic and the well logs and everything. You get a good idea of what's going on in these unconfined systems and how they're actually relatively heavily channeled. You can make the play basically using amplitude and AVO. Here's a basic cross-section of Brazil. You can get an idea of the tertiary sands right up in here. That's where they're making the play. But they also have Cretaceous plays down in here. This is going to be your play, and they're currently making in the lacustrine turbidites below with synrift turbidites below the post-rift unconformity surface. I'm not going to dwell on that, but I did that basically kind of give you an idea of what goes on in Brazil. Brazil is a very, very good province. It's supercharged. That's why you're getting so much oil there in their big fields. This is one of the types that Carlos Bruns talks about, the type 2 unconfined sand-rich lobes. They're heavily dissected by younger mudfield channels, specifically Barracuda Field, which is about 25, that has to be Miocene age, 25 million years ago. You can spot the reservoir top, the reservoir bay, see where the channels have cut out the reservoir in here, so you can basically see where to put your wells. And so it really helps quite a bit. Here's what this line up here is represented by that geologic cross-section. Extrapolate from the geophysics and the geology, you get this down in here. You see it's not one big sand, but you get an idea that this fan has been chopped in a hole with a channel here, and you get an extended piece of the lobe over there. We're going across the big pond now. We're going to work our way into West Africa. This is taken from Duncan McGregor's talk. And what he's showing you here is the ages of these turbidite plays. These are plays made since 1995. We'll come down here to the Congo first, we'll go into Zafiro, and we'll work our way towards Jubilee and these areas up here. I'm not going to talk about these, and I'm not going to talk about these because it adds about 20 minutes to talk. I don't want to do that. But here again, you get an idea of what the basic play is. Stratigraphic distribution. How does Brazil compare to West Africa? This really tells you pretty much the picture. You get an idea the Brazil margin is more located from early Miocene down all the way into the Sedimentary and Coniocene, where the West Africa margin to date and who knows what will happen as you go down the road, are mostly in the Paleogene, a little bit from the Cenomanian and Coniacian. Forteza is making this play onshore Senegal, hoping to get some oil there. Play breakers since 1995. These are the giant oil discoveries made in deepwater sands and non-marine environments. You get a basic idea. He color codes deep water versus fluvial, glacial, marine, and lacustrine. I'm going to discuss in here. I'm not going to worry about what happens over here, what happens up in here. There's the Tupi field in Brazil, so you get an idea where Tupi was. That's a 4 or 5 billion barrel recoverable field in the carbonates. How it relates to these things over here. By the way, they're just now starting to make the Tupi play over here in West Africa. Practically all these giant oil discoveries were made in deepwater marine sands and non-marine environs. They're mainly sloped channels. Distal sheet stands still remain a frontier play, although they're doing that now basically with mahogany. Mahogany is now a field. It's called Jubilee. And what you see is as people have made the play, it's like the Gulf of Mexico. You started out with a deep water shelf, and then with robotics, and you kind of inched your way down to the middle slope, and then finally you end up in an area like Jack Field down at the base of the Continental slope in 7,000 to 8,000 feet of water. And they're doing the same thing in the West Africa. It's very deep water here in Jubilee Field. The companies are moving away from the structural trap paradigm that they've been stuck in the Gulf of Guinea. Gulf of Guinea is very much actually structural stratigraphic traps, but the traps are mostly have a large structural component. Strat traps have been primarily found using DHIs, and nobody's really trying to find stuff without DHIs. The Jubilee and Zafiro oil discoveries clearly indicate the lateral stratigraphic sealing potential of hydrocarbon productive turbidite systems. This is Girasol field. This was the second large field, I think, or third. I'm not sure, because Bonga field was found pretty close at the same time as this. And the French basically found it. We're using the Zafiro as their analog and made this play. This is in the Congo. I believe it's Miocene sands, but I've forgotten. Again, keep an idea. The dot we're playing is right there. That's where we are. It's all in Angola. It sits right here. So it's offshore Angola. Nested channels, amalgamated nested channels that sit in a major submarine canyon. This appears to have some structural closure to it, the way it's set up. Now we'll move over to the Gulf of Guinea, which I'm actually most familiar with all of these because I was involved in the discovery down in here. I came aboard as a consultant at UMC in late 1992, the last quarter of 1992. I was asked to map a thin seismic grid over here that showed giant toe thrusts in this area over here. I had some lines across Alba Field as an analog, but Alba Field had very poor seismic data due to the fact they had 3 major gases coming off the top of that field. I mapped this area in here and I actually had 4 or 5 prospects. One of them was down here. It's called the Delta structure, which was somewhat of a lookalike to Alba. It did not work because they never got down to their objective. The second well they drilled was with Zafiro, which probably should have been their first test. They avoided drilling that test because it was up close to the border. At that point in time, the border wasn't fixed. There was always a question of how much was going to be in Nigeria. And people just, political risk is the biggest risk you can have in an area when you go in. And people get very antsy about that. Now, when I mapped this area, Apollo, Jade, Ruby, Topacio, and Zafiro, all these things were prospects that I had mapped, but I didn't map it as one field. I mapped it as several little prospects that could amalgamate, maybe get as much as maybe 300 to 400 million barrels. I'd given Zafiro about 250 by itself, but I'll tell you, I had to get my bicycle pump out, pump the hell out of the reserves to get up 250 million barrels. As optimistic as I was, it reminded me of my old chief geophysicist there in Midland. He says, when he saw a map I'd made, and this wasn't very optimistic, he says, Getz, you got to have a lesson in the oil business here. He says, when you map like this, you got to be so optimistic it stinks and you feel guilty about it, and even then you aren't being half optimistic enough. And as it turns out, he was right, and here's a good example of it. The other example was the other large field they found. This is the largest field in Equatorial Guinea. The other large field I got involved with is Sean Field, Guatemala, which was originally found by Texaco and offset by 3 dry holes until I came back and got a second producer, which led to be a big field, 100 million barrel field. This is about a 1.2 billion barrel field. What set this up, and at the time I was working on this, and it originally was the only guy working on this, it turned out to involve also the second stint when they actually shot the second 2D and came out and start to map it. I was mapping Block B. Joe Davis working Alba Field in this area down here, and Joe Canales is working the Block A over here, which they drilled the dry hole on. And Alba Field wasn't that big a field. Alba Field had some perched Perched water contacts in the field that eluded people. People just couldn't figure that out. So does Zafiro, by the way. Both of these fields have perched water contacts, and that's what makes this field somewhat enigmatic. And understanding those perched water contacts, you should understand it if you're going to make the deep water play. If you don't understand the concept, you're going to have problems. You're going to misconstrue what you have. Anyway, Alba Field sits as a, I don't know if I get the next slide coming in. Oh, this is just the next slide over for Zafiro. What makes Zafiro Field so big? Originally, people thought, well, your Cretaceous is too low, and that's where your source rocks are, and they just couldn't perceive of a source rock there. And I got to admit, it was tough to find a source rock there. I just presumed something was coming out of these overpressured shales, and that's exactly what happened. What's happened is you've taken this much source rock, and you've toe thrusted it to the point where it's this big. You've turned it on end with these source rocks in it, and then you cut a canyon right down through it. This section here is all overpressured. This is normally pressured to slightly overpressured. Any oil that came out in here fed directly into those canyon sandstones and filled them all top to base. They were drilling 100-foot thick sandstones, boxcar sands that had 32 to 35% porosity, a Darcy to 2 Darcy permeability, and you could map them using amplitude and AVO. When they first had the PALEOCENE-EOCENE down in here, it had a minor gas cap here, and of course that's a gas cap on Zafiro. They had problems selling their deal, and I noticed there's a mud volcano at the top. They showed, I guess, 4 or 5 companies. Now remember, I came as a consultant. I wasn't an employee, so I just came in and made my maps, wrote the prospect summary, and then left. But after they had non-success selling Zafiro, they said, well, we can't sell Zafiro. And I said, well, what's the problem? Well, nobody believes there's an oil source out there. They just can't, they have a hard time getting source. And I said, well, you can end that real quick. You got a mud volcano at the seafloor at Zafiro. Why don't you go out and sample the area around the mud volcano? If you get any oil at all, it's going to tell you you're going to have some liquid hydrocarbons down there. And I said, that's what you want to do. Well, they sent a sniffer ship out there, and the whole seafloor was covered with oil. The next people to walk into that and look at the deal after that was Mobil Oil. They took the deal. They took, I guess, all of it. And it was a third for quarter deal, and they took the other 3/4. Zafiro, UMC kept 1/4 for themselves. Anyway, I've been involved in the discovery of several large fields. They're always larger than what I expect. I really thought this may be 150 million barrels, maybe 250. Really got lucky, but I had grossly underestimated this, as well everybody else. But the key is, again, overpressured shales, source rock in the shales, bleeding in the canyon. That's what builds a long column, because hydrocarbons migrate from high pressures to low pressures. They're going to migrate in that direction. They're going to fill whatever the first thing is. And actually, some of these hydrocarbons went all the way up to EDOP field. This is a $500 million barrel field up dip, and I knew that field was there when I created this prospect. Okay, this is from an old paper that I wrote the geological portion of this paper, written by Bruce Getz, Wallace, myself, and Ron Wallace, in the Oil and Gas Journal. If you want to understand how the petroleum system is working in Equatorial Guinea, it's a good paper, basically, to see what's going on. Again, up dip extensional here, and that's what most people consider be Nigeria. Down dip translation, you get these mud diapers down, you get plays down here. Then you got Zafiro. It doesn't look very big, but you have to remember the scale of this diagram. And then Alba Field over here. Alba Field is several TCF of gas plus a $500 million barrels of condensate. That's 1.2 billion barrels of oil. Alba Field looks like this. There's your seeps over the top. You can see why people had trouble locating the wells. Again, this is mainly gas and condensate, and I suspect the reason why you have that is I don't know exactly what the source rock is here, but it could be coming from Cretaceous or something in the upper Cretaceous sourcing this. Your toe thrust prism's out in here. So I don't know you have the same source rock. Here you do here. And Alba is a strange situation because you have an inverted pressure situation where you go through high pressure back into normal pressure, and Alba Field's normal pressure, even though it's in deep water sands and they're amalgamated. Those are 100-meter thick sands in Alba, and they're boxcar sands also. We come to the Turonian next. We're working our way up West Africa. This is what during the Turonian, what things look like. You had the mid-African rift going through here. We'll be looking at this area specifically right in here. We'll eventually work our way up into there. And this is taken from Anadarko Petroleum's website. Gives you a basic idea of what the stratigraphy in the system looks like. You start here with the breakup unconformity. You get a major Sinonian unconformity, and people are just starting to really understand this in Africa. It's a major unconformity also. It's the one that seals off East Texas field. in East Texas Basin. It also sealed, which is what, 6 billion barrel field. And the same unconformity seals off the largest gas field in the world, which is North Pars Field, and its extension, North Pars Field, which sits around the middle of the Persian Gulf. LARAMIDE unconformity is also a big unconformity in there. Okay, now we'll go into the regional geology, kind of figure out what's going on. Again, Tullow Oil's site. I got this off Tullow's old site. They showed South Tano High. They bought into this deal, I believe. Jubilee Fan sits right in here. What you have is this, I think it's Romanche fracture zone, I'm not sure. And you built a big fan in here, and the source rock invasion occurs right through there. And you got source rock and reservoir relatively intercalated, if not located a little bit above or a little bit below. But it's an ideal situation. Anytime you can get a situation where source rock and your reservoirs together, especially when they're massive, you're talking John Oilfield. This is when it was called Mahogany. This came off their old website. I forget what the date of it is, but it was called Mahogany now, and the Mahogany had Tullow operated here and Cosmos operated over here. This field's made Cosmos company. Give them credit, they looked in the right area. And this field's not easy to see on seismic. You can see it as well as a bright spot down in there, but it's got a very large stratigraphic component to it, especially in this direction. This is one great big fan that's been loaded, or amalgamations of fan. It sits right here. You can see it right in here. They use amplitude and AVO to help mitigate the risk. Here's what it looks like on a combination structural map. I'm not sure if that's seafloor or the actual horizon itself, but look at the amplitude you're getting in the reservoir bearing interval. And that amplitude's all turned out to be good. That's near offset stack amplitude extraction. Now you go to Jubilee Field, that Mahogany became Jubilee Field. Okay, and you get an idea where it looks. Here it is right in here. Again, you're right there on the planet. Jubilee Field sits right in here. These, I don't think, they just happen to be very bright sands. I don't know if they made a play out there or not. As far as I know, the only production they're getting right now is here. Where are they located paleogeographically? At the base of the slope. So you're looking at very close to the junction of the source and the rise, if not on the very lower slope. It's a very ideal place to look for massive sandstone deposits. The farther you get down the slope, the better chance you're going to have having sandstone deposits. And so they're calling it a slope fan complex, but I think it's kind of a base of slope fan complex. Again, discovered in 2007, water depths 1,300 to 1,500 meters. They put reserves at 1.2 million barrels, but I think that'll go up. And it's in Turonian age fan sands. Well, if you've got a Turonian sedimentary source rock and you got Turonian fans, well, duh. The oil migrates from the source rock and the fans, and that's where you're getting it. 37 API. First oil, December 2010. It's already, I think I got it online now, 60,000 barrels oil a day. And it sounds dumb, but let me tell you, a lot of people didn't see it. Give Tullow and Cosmos credit for doing it. What does it look like in an actual, an actual log? This is the log. This is after Cosmos was bragging about what they did, which they well should do. Here's a seismic marker. You got upper mahogany sands. This volt bearing the lower mahogany sands. By the way, not all these sands give you bright spots. Some of them are very weak, if anything at all. But the net oil pay here is 95 meters, is greater than 300 feet. Individual pays from 35 meters, greater than 100 foot thick. Excellent reservoir characteristics. The deliverability of mahogany 1 tested at 20,000 barrels a day. Well, at current prices, even if it dropped down to $50 a barrel, they're going to make money. Okay, we're going to start. We've come to here. We've talked about Jubilee. Now we're going to work our way around over here to the Sierra Leone and Liberia discoveries we have here. We worked away from here. Now we're working our way to here. Here's the Venus B1 discovery, had greater than 45 feet of net pay. Mercury discovery, greater than 135 feet of net pay. And this is all these different fans shown by way of, I don't know if you can see them far in the distance out there, but they're shown by way of reservoir age. And I think there's the Anadarko block sits here in blue. The Monserrato well is down in here. Here's a Jubilee unit for scale, so you get an idea of how big some of these fans are. Recently, Anadarko, I think, dropped all if not a lot of the blocks, especially the ones that didn't appear to be prospective. And why do you do that? Well, they got oil here. It may be more difficult to get it out of here than this Jubilee because you may don't have as much stacked sand. But also, they got a lot of gas there in Southeast Africa, and Japan's a big source, big endpoint destination for that gas. So I think what they got too much on their plate, so they decided to leave. And here's what these things look like. That's a Venus there. It doesn't look quite as good as Jubilee, and there's Mercury, which doesn't look nearly as good at all. But it gives you an idea of the 34 to 42 degree API oil here. Here it just doesn't have much reservoir to it. The amplitude looks good, but remember, you're going to get some good amplitude off of high quality reservoir sands, and some of them will actually give you an AVO. So it's not all shooting ducks in a barrel. You're going to have to get a little luck involved there too. Now we're moving into Nova Scotia and Moroccan continental margin. These are the frontier deep water plays, and actually to me they look very good. People are they're starting to play there, but some people understand it, some people don't. I don't understand it totally, even though I'm talking about it. This is taken from a Vanco 2002 presentation published on the website, and what it's really showing you is you've taken two seismic lines and juxtapose them to get an idea of what the salt and what the different age of formations is, and it just looks like two halves of a hole. And remember, up dip up here in Nova Scotia, you got Panuke Field. It's going to produce close to a TCF of gas plus liquids. So, and that's Jurassic carbonate, so good chance you're going to have a Jurassic source on both sides of that area. In fact, you know you got a Jurassic source to the west around Morocco, and that's key in the play. Second key in the play, and this is what most people don't understand, and the next slide will drive things home even more important. Okay, similar sands are found over the entire Northwest African passive margin. It could be a major potential reservoir. What they've done is they've had some volcanic uplifts along the western margin. They've pushed these up to the point where they either outcrop or very close to the sea floor. And you've got some massive sands out there that are very early Cretaceous age, Perbekian or whatever. West African, is this the West African version of the Whopper Basinal fan? Could easily be. In which case you're going to get multi-story oilfield units. They show the source rocks down here in Jurassic, but you also have late Cretaceous, or they call it late Cretaceous, actually, I would call it middle Cretaceous. You got a billion-barrel accumulation heavy oil in Dome Flore field, which is in Oligocene tempestites, which is basically another carbonate field. But you also got some Neosine discoveries up here, like Chinguitti. But the real play we're going to make is this one here, and that has not been premiered. But I'm going to show you something on the next slide. This is really telling you a story. What I've done, I've moved from here to here. Well, that's an awful big jump. That's really away from Nova Scotia. It's kind of a different part of the plate. Yeah, it is, but there's your Nevada nonconformity. Okay, right through there. You've got, that's Lackfield down there, which got a god-awful amount of gas, like 8 or 10 TCF of gas in there. But some of the fractures, carbonates above it, which kind of form a partial seal, fracture, and you get some in the lower Cretaceous. That's where some of the reserves are coming from. You get oil above and below mostly above the unconformity. But look out here, this little lone ranger no one's ever really seen. What is that? That's a Perbekian sandstone. What's that? Basal Cretaceous. What are these? Basal Cretaceous. What's our source rock? Jurassic. What's our source rock? Jurassic. Now, you're in a different plate tectonic situation here than you are there, because this is the Pyrenean-Forland Basin, and the other place was a passive margin. But if you're looking for stuff, if you're looking for a place to get into, Shell's already looked at this, and they're looking off Nova Scotia, and some other countries are playing down through here. Good place to be sniffing around. Now we'll go into Nova Scotia. We're getting very close to the end of my talk and starting to wear on my voice. I hope I'm not getting too low. We'll talk. Now we're up in here. You can see where we've been up in there. Here's Panuke Field. Again, that's about a TCF of gas equivalent, but it has some liquids with it. You see deltas down here, the Laurentian delta and the Laurentian and the Sable delta, Shelburne delta, and you have this carbonate bank that sits between them here. This is a structural stratigraphic trap. It's not pure structure. It took guts to drill this, but and they still haven't produced it yet that I know, but they're getting ready to. This is late Jurassic, about 150 million years ago. That's in the carbonates. But look, early Cretaceous, you got deltas coming down through there. Where you have that Jurassic source rock, if you get structures out there, you're going to make a play and get it. That's what Shell's doing, I'm sure. Okay, Chorus prospect. This is one offshore Guinea-Bissau. I'm working with Forteza in this area up in here on their onshore acreage, so I know what goes on down here. The AGC Profundo block. Profundo is French for deep. There's Dome Flore field. They decided, well, we come down slope and find a place that's got amplitudes and maybe and big structure, maybe we can make a play. But it didn't work. Well, let's take a look and see why it did not work. Huge structure, 226 square kilometers, almost too huge in my mind. And you look over here, great amplitude. Some of them kind of give you a little bit of AVO, and you get a great CSEM anomaly. You go, God, man, this is mother load. We're going to get rich. But if you start really looking at the slide, what are you looking at here? Where's your reservoir? Reservoir is over here. You can see it, all these channels, that's where your sands have been funneled down through. Up in here, unless you're dealing with basin floor fans, it should be thick here rather than thin. Most likely what you're going to get is some thin carbonates and marls, and where you get a pressure boundary associated with that, you're going to get an AVO, and that's exactly what they hit. I figured this out early before the well was drilled, but I wasn't really involved in the prospect. Okay, we'll come to conclusions. Besides that, sometimes I'm wrong. It could have been a big discovery. Who knows? Basics of the Circum-Gulf of Mexico hydrocarbon plays. I got two conclusion slides. One is on Circum-Gulf of Mexico. The other one's on the Atlantic origin. First world-class giant oil field was actually onshore Pozo Rica field. It's in carbonate four reef debris. Again, nobody's making four reef debris plays now that I know of, except for possibly Tengiz field. They're doing that. That's a big field, but there's good reasons why it is. Cantarell field is the largest field in North American continent. It's in a structurally pooled in Cretaceous carbon debris. Again, carbon debris, upper Cretaceous age, but it's actually Paleogene because it's a blast debris generated by the Chicxulub bolide impact. You got a multi-billion barrel hole of heavy oil accumulation has also been found in Chicontepec sandstones right here. And then you've got late 1980s for early 2000s, people are slowly moving down the slope from the Miocene sands all the way down into the Paleogene sands to make a play there. So that's what's happening right now. The future play, Bahamas. Atlantic margin conclusions. Basically, the Circum-Atlantic hydrocarbon plays in deepwater clastics. And I'm pretty much talking about these right here. I include this because it is an Atlantic. Giant Circum-Atlantic margin oil fields have been found in deepwater sandstones fronting the massive passive margin delta. Remember, we have a Cretaceous age delta right in here. Ranging from early Cretaceous to Pliocene age, these oil pools appear to have been mainly sourced by late Jurassic to Eocene exotic sediments. Now remember, the source rocks that sourced Zafiro field, I believe, are Eocene age. Eocene. No one foresaw that source rock before they actually sampled it in one of the wells and actually figured out it was there. But late Jurassic also. How do you figure out where the late Jurassic source rock is? Well, if you got penetrations up here and you got Jurassic oil, you know that. But you also have Jurassic oil down through here. Oil and gas companies or hope to be there. Oil and gas companies have been expanding their continental margin operators. They come north from the West African Dike. That's what's happening. They move north from here, and they're moving north from Brazil. And here they're going here to here. Here they're going here to here. It's a natural progression because that's what acreage is available, and they're doing it in rock cut areas in many respects. You got multiple Jurassic and Cretaceous soil sources coupled with potentially thick Jurassic and lower Cretaceous low stand tract sandstone deposit appear to make the Morocco Nova Scotia conjugate margin an attractive target for future oil and gas exploration. There's reasons why some of the biggest companies are making that play, and they're good reasons. Reservoir may have a problem. I can't testify as the quality of the reservoir when you start getting in the deep water. Since a lot of these fans have been extruded onto thin continental crust or even oceanic crust, the heat flow is not so great. Consequently, the reservoir destruction is not as great. That's what you have in the WILCOX sandstones. That's why you got oil in the WILCOX in the frontal lobes of those fans in the Gulf of Mexico. But you go up on the slope, it's all gas, and it's almost C1 at that, or C4 at that, or methane. Oil companies are getting more comfortable with operating in ultra-deep water environments, so they're gradually moving down the continental slope into modern-day ultra-deep waters near the junction of lower continental slope and rise. What's that? Well, that's robotics. Without robotics, you wouldn't be able to make these plays. The guy in a hard hat couldn't get down to the area around Thunder Horse or at Jack and those discoveries over here. And I put this caveat in there so you realize we're not really looking for oil and gas. We're looking for money by finding oil and gas. Oil fields that cost $200 to $300 million per well to complete could have poor economic returns in the future. Example, Jack and the ISIS field. If oil prices drop radically. I don't know if I left one more slide in here. Didn't. And I thought I'd leave the other one in there. But that slide was the one I showed you, my smackover talk. Y'all want to see that slide?
Yeah.
Didn't know. It's all the way down here somewhere. Tell you what, let me escape. Figure out where I am. You'll see it on YouTube. I won't show you this slide here, which will depress the shit out of everybody. I'll show you this one right in here. I've been around this business since 1968, and I've seen 2 booms, 2 busts, and now I'm verging on what I think is the second bust. But I'm glad to be in the second boom because I'm making a lot of money. Okay, we go back down to, how do I do this? Okay, this is difficult to see, but I'm going to leave this up for those people in back. Most shale gas is uneconomical below $70 a barrel equivalent of oil. Most of them are uneconomical now anyway because of gas. Most deepwater WILCOX oil is economical below $60 a barrel. You're sucking wind. You start drilling $300 million wells, drilling complete. $60 barrel, that doesn't make sense. And then that's a minor price decline. Not big, minor. We've seen it down close to that. Significant price decline. Look at all the things that don't work anymore. There's a bunch of them in there. Major price decline. All these don't work. Devastating decline. All these down here don't work. Most of which kind of work now. So keep this in mind when you're making your play, that when you're looking for oil and gas, when oil price and gas price are going up, you can make a mistake and the price will bail you out, because even though the oil field's not as big as you thought it was, the price bails you out, you get more money back. But it does exactly the opposite when the industry's in rapid reversal. That is, if you bet on it being such and such size or such and such price and the thing drops in half, you're devastated. Well, that's the end of my talk. Any questions?